Today is October 19th, 2019, and this is the John Chappell Natural Philosophy Society Science Chat. And the way this works is that you can be watching us on YouTube or Facebook. I prefer you be on YouTube so we can keep track of who all's watching the broadcast. And if you would like to come and participate, you can come into our live room, which is live.naturalphilosophy.org, and you can participate in the conversation. So this is supposed to be a science chat, so I see we have 3 people in our live room. We have Bob and we have Michael. So if you wish to talk, please get my attention by turning on your camera and waving at me or putting something in the private chat. And then we can get you on the show and talk in here. Because all I have to do is just, let's say if I wanted to add Bob, I could add Bob there. And Bob doesn't have his camera on right now, but I can add you such that you can talk as well. So why don't I try that? So I've got Bob and Michael here at least. So if I do that, I can still add them to the stream, but not to have them show up on video, I think. So Bob, can you say something so we can hear whether this is working? Now let's see here. I don't hear anybody talking. That could mean that I just don't have things set up correctly. Let's see here. Bob, are you there? And Michael, I see you undid your microphone there. Okay, let's see now. So for some reason I didn't hear you, which is kind of weird. Well, try and talk again. You are talking. Well, I can't hear you at all. And we have some comments from that R3N. How about this, Bob? Can you hear me? Okay, you can hear me, but for some reason... Okay, I'm going to put you on the screen. Maybe that's the problem here.
Hello.
Hello.
Okay, it looks like I actually have to put you on the screen. I was trying to test to see whether if I put you just in the background without your picture, whether we can hear you, but...
Right.
Well, now I can hear you, and you're not full screen.
Oh, that's strange.
Okay, so that works. And we got Michael and Teskey. Michael, can you say something? And we've got Bill Lucas here. Good morning, Bill.
Good morning. Can you hear me?
Yeah, we can hear you. So good to have you here. So what I'm going to do this as an experiment. So I'm going to see whether I can keep you guys. You'll be live on the stream, and so you can talk anytime, kind of like when we had Fuse, I guess. All right, so you can see me. So say something, Bill. Yep, that works. All right. So we're going to try it that way. So if you guys want to interrupt, let's just like old times and Fuse. Well, I guess you can try and do that. All right. So we've got Alistair here as well. But I thought I would start the conversation here with some of the emails we had gotten. Now, we had briefly touched on the topic of evolution in the last science chat, and it kind of created a little bit of a email storm about evolution. Although, curiously enough, I think everyone on the email chain would
generally speaking, disagree with the concept of evolution. So there wasn't that much controversy, but I thought I'd share some of the messages that I'd gotten this week. Let me see here. Chrome tab. Let's see here. Here we go. Now, it did kind of devolve into more of a religious discussion here. And there's a discussion about, you know, why did God create Adam and Eve, and why did he create the tree of knowledge, and why did Adam eat after Eve, and stuff like that. So usually, though, I'm not too crazy about when people start sending just purely religious stuff about on these emails, but that was a good part of it. But I guess this is kind of typical. So let's run through the logic. God initially creates Adam and Eve, possessing absolutely no knowledge of what's good or evil. So why do that in the first place? Someone who can't tell the difference between good and evil is considered a psychopath. So does this mean that Adam and Eve were psychopaths? I'm not exactly sure I would agree with that particular interpretation. If so, why would God want to create psychopaths? Okay, moving on from that. Then he plants a tree that if they eat the fruit, they will no longer be psychopaths. But then he tells them, or okay, he tells just Adams, that if they eat the fruit, he will kill them. So he wants them to remain psychopaths and just sit around eating other fruit and doing no work. That's got to get boring. But if they do something to cease being lazy, psychopathy threatens to kill them, but in the end, cast them out. Now knowing the difference between good and evil, but now have to work. God sure does work in mysterious ways. Can someone educate me? So that's kind of funny. I don't know what sure that has to do with anything about science or evolution. I think there were some other comments more relevant to evolution per se. Let me see if I can find one of those threads here, because there were actually a couple different threads going on here. Some of them having to do with evolution, and more having to do with, say, how birds became dinosaurs and things like that. That would have been a little more relevant to that whole thing. Let's see, where's some of the older ones? Some of them were kind of funny. People were pasting in pictures of stuff. Oh yeah, there's this argument here that automobiles showed evolution here. See, all automobiles evolved from below Ben's original, and all later designed and developers are analogous to the evolution mutation process. Some worked, but many didn't. So, except I suppose that we know for sure the automobile was a process of creation, intelligent creation, I should say. And that was like my original point, that when you've got things that are changing, you know, these things have the same common things like motors and wheels, and the way these things evolved was that people intelligently decided which features were better and kept those. So in that way, it wasn't really a random process. So that was one interesting thread here. But my comment here was that evolution, as observed by Darwin, seems to be limited to only accentuating features of an existing species. So wings can get bigger, colors can differ, they can get bigger or smaller. However, evolution cannot modify a creature to be a completely different species or type of animal. They have done experiments where they try to evolve some characteristics, like the number of hairs on a fly, and it can only go so far before you get something that simply cannot reproduce. So while Darwin correctly deduced how birds might differ, the birds did not turn into dogs or any other significantly different species. It is still a bird. I'd agree there is little evidence of species becoming completely doing a transition, becoming completely different, and what Darwin observed was just these slight changes, and it didn't really account for origin of, like, say, completely different species. So, like between apes and humans, you know, that's a pretty big change. And while Darwin observed, you know, birds having different beaks and such, you know, that's the extent of the change that's possible. It's still a bird. And so if you guys have any comments, you know, please feel free to break in. I'm sure, Bill, you must have something to say about this.
Well, the comment I would make is that from the review of the everything being dependent upon the electric field, and the electric field version is God, not charge. Charge is just a mathematical proclamation to simplify some of the equation. So that would be a different concept. But everything is composed of solitons of the electric field. So all particles and forms of matter, all charged elementary particles, everything comes that origin.
Let's see here. I'm having a hard time hearing you there, Bill. Maybe you need to get a little bit closer to your microphone. Let's see, we got some comments here. Bob says, "Can we talk physics?" No, this is the problem this week, is that the entire email chain got taken over by religious zealots is the problem. And Michael Antesky says, "My model correlates the religious with physics through an ether model." Yeah, Michael, did you want to comment on that? I think we can hear you if you talk. Are you talking, Michael? Let me see if we can get you up there. Let's see if I can plug in my microphone here.
Are you trying to say something, Michael? Because if you are, I can't hear you. Let's see here. Well, we have some additional comments here. So Ian is here, but he can't be heard or seen. Well, Ian, you need to go to live.naturalphilosophy.org, because right now you're on YouTube. So if you go to live.naturalphilosophy.org, you can join us in the live room, and you can participate in the discussion. Okay, well, going back to the mail here, I think one interesting thing that was brought up is that chimps have 24 pairs of chromosomes, but human beings only have 23. So the argument here is that since chimps have more DNA than us, then they must be more evolved than us. In fact, chimps must have come from humans, perhaps, because they obviously have more genetic information, which I didn't know. But that is at least something that's physical. So we can get back to talking physics. That, what is the physics of DNA? And if something has more DNA in it, does that make it more evolved? Maybe it does. I don't know. That would be kind of weird, right? But I thought that was an interesting point that was being brought up. And let's see here. Like I said, there's mostly arguments here saying that we haven't seen any transitional DNA or transitional animals here. And I suppose the physics part here is that this is what we often do in physics. We will observe things, and then we'll try to ascribe a cause for those things. So physically and scientifically, we can categorize all the DNA of various different species and fauna, and when we do that, we can draw up these nice trees showing that how the DNA appears to be modified from one creature to get the next creature, and we can see what the family similarities are. So from a scientific standpoint, it would seem to make sense that these creatures came one at a time, I suppose, and that suggests that there's this evolution process where species are changing into different species. But we, generally speaking, don't see a smooth transition between species to species. They just seem to just all of a sudden switch into something else. So, but since we were not around to observe that whole process, I suppose I can neither confirm nor deny whether that happened. And if there aren't any transitional species, well, maybe that's because they just didn't last very long. I mean, it's remarkable that we have anything remaining after, you say, millions of years from anything. So if the transitional species only lasted for, maybe 100, 200 years, then it wouldn't be terribly surprising that we don't have any evidence of that. Or the other thing I've heard is that these evolutionary causes are actually caused by, say, mass extinctions. And that what happens is that, the species that are dominant will remain dominant until one of these extinction events. And then when that happens, then the other creatures, which, may have just kind of been in the background, suddenly become the dominant species. And then we see this sudden switch from species to species. So that's another way that it could have possibly happened. But enough on that, I think. Let's see here. What other interesting points were there about that? Well, I guess we've got this evolution is just really a monkey and a typewriter argument. And there's some talk about who are atheists and who feels scared. And once again, it's like the entire email chain has been taken over by religious zealots. And yeah, some people have been putting some interesting cartoons on the web. Well, yeah, so a lot of talk about evolution. So let's see here. Now, let's see. I'm going to stop screen sharing there. There we go. Let's see if we've got any comments going on here. let's see here. So, Michael, you were trying to talk, but we were not able to hear you. Let me see if I can put you back onto the stream here. So, Michael, why don't you try and talk? Let's see if we can hear you. You're not muted, but it may be that your microphone is not working. So, Alistair, you seem to be having the same problem, that you're unmuted but don't seem to be hearable. So that may be because you're not on the screen, but I think you are on the screen. We've got Ian. Ian, how you doing there?
Thanks, Falcon. I think I've solved the problem. I was going into the wrong link. So I'm obviously in now.
Oh, great. So, I was wondering, did you have any comments about how the entire email chain got taken over by evolutionists?
I suppose I do, yes. And I just made a suggestion in the box there that you might sort of almost twist our arms, maybe at the beginning, at the end, to give a few comments and even to summarize, you know, even if we don't volunteer to speak, a bit like Glenn Baxter used to do in the past. But anyway, thanks for giving me the opportunity. Now, I think I've told you on past occasions that I'm not really a sort of an emailer. I don't like all these panoply of emails coming in, so I haven't read them all. However, I have glanced at them, and I have noticed indeed most of them are on evolution and on Genesis, and various views are being given and so on. Well, to be a bit blunt, I do agree that this is hardly physics. On the other hand, even to be blunter, to me, it's just like going into the details of talking about whether Thor ought to have said this, or Odin ought to have said this, or what he did. You're arguing about a particular religion. It happens to be, you know, one of the Abrahamic religions, which most of us in the West adhere to. But to me, it's trivial to start arguing about these things. I mean, you know, you either believe it or you don't believe it. And I think the views are rather polarized and, in fact, quite extreme. You know, you get quite harsh comments coming from both sides, from the sort of, you know, traditional believing type of people and the non-believing people. So I haven't contributed to it. I thought it a bit jocular in ways, and I'm interested in one or two of the emails. I haven't got the time to go through them all, nor do I have the inclination. Just about evolution, I have said one thing in the past, which I might repeat now, that I personally think that maybe there's something missing that we haven't yet fully deduced, and it's related maybe to what was disposed of at some time in the past, which is sort of a Lamarckian view of you know, inheritance of acquired characteristics. And this idea was sort of put out that there were just merely random changes in the environment, which some, maybe a very small proportion of which were beneficial, and they were selected. And that seemed rather difficult from a probabilistic point of view. Now, Darwin himself actually did believe in the inheritance of acquired characteristics, although he did believe it was a minor part of the natural selection process. But this, as far as I can see, has re-entered into modern biological science. I've forgotten the name for it. They have a term. It's not an inheritance of acquired characteristics or characters, but they talk about exogenesis, and there's some name for it. And I think maybe, you know, usage, that animals actually do certain things which are beneficial to their survival. And whether those are inherited by their offspring would make quite a significant difference as to whether, you know, beneficial variations could be put on to their descendants. So my own view is I'd like to modify the theory of natural selection with some elements of inheritance of acquired characteristics. You might put it in the modern term, because that's a bit of a pejorative term, but So anyway, those are my only comments about the whole process, and I think there's no harm in maybe touching upon it. But to go into such detail about, you know, a particular god, the God of the Old Testament, which is true that most people in this part of the world, the Western world, believe in, but that doesn't make it any more valuable to start arguing about it. You know, we might as well argue about what Buddha did, or what Confucius did, or what, as I say, Thor or Odin did. So those are my big comments.
Well, I was wondering what you thought about, say, the observation that chimps have more DNA than we do, and that's kind of suggesting that that perhaps chimps were evolved from humans. I mean, that is a physical thing that you can't observe. So, and it kind of contradicts the idea that humans came from chimps, I suppose.
Well, of course, two things there. One is, I think this has been mentioned in one of the emails already, that more chromosomes doesn't necessarily mean further development. You know, you could have fewer. The other thing is, I think basically the traditional orthodox view would be not that chimps are the ancestors of humans, nor that humans are ancestors of chimps, but that chimps and ancestors have a common a common primate ancestor. So, in other words, the general parody that you know, we're all descended from monkeys, that is not you know, the traditional evolutionary view. The traditional evolutionary view is that monkeys and humans have the same primate origin.
Yeah, that would be part of the science of evolution then. But yeah, that's good for pointing that out. So there is definitely, you know, a fair amount of science involved in the analysis of DNA. In fact, I think there is a particular article on that. I thought I was going to go into a little bit into science news and see what's going on there. So we're going to go on to, this is an article that I found from Google News. So, and this is about an evolution in understanding of evolution. And it looks like this person, Kristen Nayo, is proposing to have a way of building models and putting things into particular boxes here. Since that it's not uncommon for living things to be reclassified into another genus, as science gets better at identifying protein and gene changes. So, for example, there have been recent changes in the taxonomy of different kinds of bacteria, plants, and corals. And certainly this is a major area in the science of DNA, which is taxonomy, which is grouping different animals into certain categories. So, and they're talking about making a better model of evolutionary change that, while not being 100% accurate, could give a clearer picture. So I think that is what they're talking about here. And this is specifically a methodology for reconstructing protein evolution with improved accuracy using ensemble models. So I guess this would be very specific to proteins. Let's say reconstructing evolutionary branches is tricky, especially when many species share a similar type of protein that might have evolved to perform somewhat different functions. Mathematically, the problem quickly becomes very big, but discovering the implications of this protein evolution could lead to a better understanding of how our bodies deal with cancer and other diseases. Now that would be interesting on how they actually come up with a way of categorizing proteins such that you might say this came from that, because I don't know, a protein is like a protein, I suppose, and they're kind of either all there or not, I suppose. So how could you evolve a protein? I guess you could have a protein, then you could add some extra thing onto it, and then that, I guess you could perhaps recognize that as an evolution, perhaps trying to track that. But they say the reconstructions didn't agree with each other despite 1,000 attempts. But that itself wouldn't be a huge problem. I didn't expect them all to agree. But I expect one model to be refuted most of the time, or at least a lot of the time. So that would be like the evolution of the car, where there's some things like the steering wheel, which seems to be very much in common in the wheel. But that was an article found on Google News. Let's see what happens if I close that window there. I go back to sharing here, and if I share, let's see, just the Google News. Let's take a look at what's going on in Google News here. So this is specifically the physics tab of the Google News here. And we've got a couple things here. How about this? Could an astronaut lost in space use gravity to get around? Well, maybe to fall into a planet, I suppose, but I'm kind of interested in how this works. So you click on the link, and then it goes to the next screen. So I was wondering, are you guys seeing the Wired screen, or are you guys still seeing the Google News tab? Can someone tell me what you're seeing on the screen?
Google News.
You're still seeing Google News. Okay, so I think I have to specifically switch to the new tab then. Or I have to share my entire screen. Or I can share the application window, entire screen. Doesn't look like I can. Let's see here. Let's share just that. Okay. Okay, so now you should see the headline, could an astronaut lost in space use gravity to get around? So you guys see that?
Yes.
Okay. So what is this about this? So you're floating in space, and there's a cute beach ball sized asteroid 3 meters away. So how do you get to the rock? And there's only 3 meters. Okay, they're going to suggest what? That the gravity between the rock and you will be used to get you closer. First, the force between a rock and a person would be very, very small. And so I guess then they try and actually model this. Yeah, this is like the attraction between a girl and a boy based on their gravitational attraction, and it's not very much. And what are they saying? It'll probably take forever for that to happen, huh? So it'll take 11 hours for the rock to be attracted to the person, right? So they're doing some calculations about that. But I think it is interesting that gravitational attraction does happen between very small masses. That's what the Cavendish experiment was based on, where they basically had a sphere which is suspended on a line, kind of like in a dumbbell situation, and then you put a large attracting mass in there, and you can actually measure the force of the small ball to the large attractor mass. And so that kind of, well, perhaps partially rules out some of these explanations for gravity that may try to make it be like an external thing, like a pushing kind of thing. because if it were like a pushing kind of thing, like rain coming down from our heads, then how would you explain the small ball being attracted to the large ball on a horizontal basis, where gravity really wouldn't be acting? So it couldn't possibly be something where some matter is being sucked into the earth, and that is just pushing everything from our head down, because that would only explain the force of gravity going to the center of the earth, and not the force of gravity, say, going through two small objects like an astronaut and a rock. So in that way, it would seem that the force of gravity does in fact originate from inside of the masses. Would you guys agree or disagree with that? Does gravity come from inside the mass, or is it something external? That's certainly one interesting physics question. What do you think? I'll pick on Ian. What do you think? Where does gravity come from? The inside or from the outside?
Just unmute my mic. Okay, you've called my bluff, because I suggested that you do address people specifically. So thank you, Franklin. Yeah, I think there's a lot in what you have just said. I mean, these sort of these explanations, the sage type explanations, do apparently, or would apparently explain gravitation on a macro basis, between planets and suns and so on. But they have some difficulty when you get to the smaller aspects of gravitational interaction between two masses, such as the Cavendish experiments, as you showed, particularly small laboratory experiments, apart from experiments, say, between large masses like a mountain and a pendulum. Now, I haven't had an opportunity of really looking at that article which you've been putting up on the screen. The type is very, very small here on the screen, so I couldn't really read it. So I'm not quite sure what they're getting at more than that. But I do think, as you say, it does pose some problems for the sort of particular type explanation of gravity. I don't know what you feel, Franklin, yourself and others, because you promulgated the possibility or the probability of an electrostatic explanation of gravity. So I don't know how you feel it fits in with that.
Well, I feel that the force, if it's an electrostatic, can easily be demonstrated, because I can, if I have a Van de Graaff generator, I can completely defy the forces of gravity by just charging something up, and the opposite charge will actually cause like a stone styrofoam peanut to actually fly up and away. Or if you've seen the demonstration, people put their hand on a Van de Graaff generator to have very long hair. All their hair just stands right up on end, seemingly in defiance of gravity. And they have done experiments where they just take what appear to be, just ordinary objects, and they fire them in this like zero-G cannon. So the objects go weightless for a few moments, or actually I think they've even done this on a space shuttle. You just take any random group of objects, and they will just clump together. Now, mind you, the amount of mass in these tiny objects is way too small to account for really even any kind of gravity. I mean, if it was gravity, it would take even longer than 11 hours for those things to come in. But no, basically they come together almost immediately. So the only force that's really available to do that would be the static electrical force. And so that's what I am basically proposing is gravity. In the case of small objects, the differential in charge can be much greater than, say, on the Earth, where it's kind of limited by basically the astronomical environment. And you would, and I would predict that if gravity is basically electrostatic, that you would find that the gravitational constant, in fact, is not constant, because it more depends upon the. You would say if gravity was charged, then you would say, well, it depends upon the amount of charge. It would in fact depend upon the type of medium that is between you and the thing that is being attracted. Because space, the charge depends on the permittivity and permeability of the what's between, and that's why I think in these gravity experiments we see people coming up with different values of g, depending on what kind of experiment that they've got going on. So that would be kind of my feeling. Now I see here. So Cornelius says that mass comes from gravity. Well, that's kind of an interesting and opposite kind of idea. So Cornelius, I'd be interested in hearing about that. So if you'd like to come and come into the live room, I think I'd love to hear you try and explain what do you mean by that. That mass comes from gravity. That would be presuming that gravity is something more of a fundamental thing, and then somehow mass arises from that. Although that would seem to be completely backwards to me. Let's see here. We've got a couple other people here. Let's try Alistair. Alistair, can you try and say something? Is your microphone working? Perhaps you're muted or something.
Can you hear me?
Yes, we can hear you. Go ahead.
Yeah, my microphone issue was I had it disabled by a key on my keyboard, and I didn't realize it. It wasn't your system at all. But
Okay,
then when
great.
I got back in, I was backstage, so I still couldn't talk. There are animals, tiny creatures with many more chromosomes than humans. You can look up a list of animals by chromosome count and see that just because apes have more, so do some fleas and crap like that. And sorry, I had that.
Fleas have more chromosomes than we do?
Yeah.
I'm insulted.
On the issue of the gravity, the person and the object, they will be attracting each other and they will be moving towards each other. It will just be at an extremely slow rate because of their extremely small mass. There are binary asteroid systems that we have observed. So we know that there are pairs of objects in space orbiting one another around a common barycenter.
Yeah, we've also done things like put satellites in orbit around these small asteroids. So definitely, even the small asteroid has definitely a usable gravity field.
Yes. As to the nature of what gravity actually is, well, then that's a whole different question as to whether or not the two things would orbit each other or not. But before you offered me, other people in the list had offered to see. Bill Lucas says he has an electrodynamic explanation of gravity, and somebody else had said they had one as well. So I don't think it would be fair to let me jump the queue, but I could certainly give everyone my version if they want it now.
Sure, why don't you...
I'm just trying to be fair.
Go ahead and explain that. I'm going to turn off my light behind me.
The way I figure it is... it's hard to explain. Sorry, I'm going to turn down my speaker. It's hard to explain in isolation, just gravity, without kind of explaining everything. I'm pretty sure most everyone here is aware of my overall suggestion as to how things work. I see that there's like this omnidirectional vibrational nature to every point. So every point goes through this motion, a vibration, call it, that after a cycle has headed in every direction. So you have to see space as filled up with points that are going every single direction, but because they're all doing it, it all balances out, so nothing goes anywhere. Then when you have breaks in that uniformity, an imbalance will always create a counterbalance in the harmony of the vibrations. And those counterbalanced imbalances will orbit one another because of the nature of the way that the whole medium works. And so you will get this gravitation. At the very smallest scale, you'll get this propensity for things to orbit other things in pairs. And then as the first pair, we're going to call it a hydrogen atom, it's orbiting each other. Then along comes the other one, and then they're going to want to get together because why? That's the hard one.
I mean, why two hydrogen atoms would want to get together?
Yeah.
Because it's interesting that, we oftentimes don't see gases in the monotonic state. We always see like O2, H2. Why is that? Why do we not just see like, oxygen and not say O2?
Well, in the case of let's use just the single. So you've got this entirely filled three-dimensional space that's all vibrating, but all vibrating in harmony. So there's nothing. So you've got this kind of empty universe. And then an imbalance occurs and a counterbalance occurs. Look at them as being whirlpools on opposite sides of a ball to create overall a torus. The torus is made out of an imbalance and a counterbalance. And so they are what is on the two sides of the torus that make it a torus instead of a sphere. They give it its polarity, and they're a result of the vibrations that fill space. And they are what creates the impression that there is something physical at that scale, but instead of it being physical, it is these balances and counterbalances that create the toroid. And because they do that, they need to be in pairs because they're matched. The imbalance or the disharmony, the discord, and the opposing counter discord, they balance each other out. And so they orbit each other. I'm not doing a good job. That's why I wasn't really kind of prepared to go. But so what do I think gravity is? I think gravity is the masking of pushes in a where every point can be seen as pushing and pulling. Then when you have something that blocks that, then things on the other side will be pushed towards it because it's blocking the push pulls coming from the other side of it. So gravity is not a force attracting, it's pushes which then cause you to float towards the center of. So if you see the Earth as a sphere and you're up there in space someplace, you're not pulled towards the sphere. Instead, you actually float down to it. If you think of space as being upside down and Earth as being it's up and nothingness is down, you will always float towards up, which is the closest, biggest thing to you. Is
Well, I
the
suppose that
center
might
of the
explain the overall direction. But one of the interesting things about gravity, that if I take something and I drop it, is that it's not just gently pushed down to the surface by, like if it was like rain or something like that. It actually rapidly accelerates towards the center. And on the Earth, that's 9.8 meters per second. And if you, don't worry about things like friction, then you kind of have a mystery on your hand of it being actually pushed. Why is it pushed so much faster as it gets closer to the center of mass?
well,
If it's some kind of a push.
think of it this way: we know that existence is granular. So imagine if you were going to draw a line from the surface of the Earth into outer space, going in every direction. The surface area of Earth is, let's use just 500 million square kilometers. So depending on how granular existence is, let's pretend it's really not that granular. Let's say that the granularity of existence is a kilometer, a square kilometer, or a spherical kilometer. So from the Earth, extending outwards into space, there would be 500 million. These are just hypothetical strings. But when you go a kilometer above the Earth, now it's not 500 million. Now it's the surface area of the sphere that's a kilometer larger than the Earth is now 25 million. The farther away from Earth you get, the more of these hypothetical strings extending from the center to reality there could be. Do you see that?
Not exactly. I mean, or maybe in the sense that as you get further away from the Earth, like if you thought that Earth was a hairy ball and all the strings just kind of extend outwards, the density of those hairs would decrease as you get further out, 1/r².
Same thing. That's what I said. You could have more of them because now they're separated. Because as you
well, no, I mean, I think you get less of them per square meter, right? They get less dense as they get further out.
They get less dense, which means that if you were going to fill that virtual sphere, remember we started off with 500 million of them at the Earth's surface. So now if you extend out to a radius where there's a 600 million square kilometer surface area, you could fit 600 million of them. When you extend out further till you've got a sphere of 10 billion square kilometers, way out there in space, wherever that is, now you could have 10 billion of them. So recognize that the granularity of existence is okay. So all right, you recognize that as you go further from the Earth's surface, the density of these hypothetical, and I'm not suggesting in any way that these are real strings, they are just mathematical to demonstrate what I'm trying to say. Imagine them now, instead of being strings, imagine they're like logs, and they're not static. They go up and down and up and down. So you got all these logs extending from Earth to the perimeter of the universe, but they're logs that are going up and down and up and down. So you got these 500 million logs going up and down and up and down. As you extend away from the surface of the Earth, there would be more logs, not less, more, right? Because now there are gaps, you can put more logs in the gaps.
Well, it depends if space is already filled with logs. See, this is the whole question I'm trying to get to is, where does gravity get its strength from? Is it an internal thing? Is it internal to an atom? For example, does an atom itself, all by itself, have gravity? So if I have a uranium atom and I put a neutron next to it, are those two things going to attract? Right?
Yeah, I recognize that I may not have chosen the best analogy, and it's really difficult to do with just words instead of visuals. And I'm trying to think of the best way to simplify it. But because the Earth's surface is curved, you recognize that as you move away from it, the surface area of that virtual sphere is higher.
Yeah, as you get further away, that's
Right.
that's fairly obvious that as you get further away, the surface area obviously
Right.
gets much, much bigger.
So
Right.
now think of logs was maybe a bad choice, but think of each of those lines extending from Earth to the extent of the universe, and let's just use Earth and an empty universe. And so these lines, as you get
Just let me interrupt you for just a second, because I think so. The challenge I had presented to you is,
Explain gravity.
the thing is that not specifically that, but why do things accelerate? Because it sounded like you have the idea that things like the Earth and the Moon, or like in that article, you have the astronaut and the rock, and they are attracted, but you're saying there's something on the outside of those things that are pushing them together. It's like, that's fine.
Right. It's not that there's like a thing pushing, it's that every point is constantly pushing and pulling. And so
how do you get the asymmetry, right? You're saying that like the rock is kind of blocking the astronaut, and then there's less. That's the classic Lesage
let's
argument.
ignore blocking temporarily. Let's just stick to this sphere with lines extending from it, and the farther you get from it, the more lines you can fit. The equation for how many lines you can fit is the exact opposite of the equation we use to describe gravity.
Well, that would just be the equation for the surface of a sphere, according to radius.
Right. The inverse square law is gravity, and the number, the number of the.
Well, in fact, that's how the 1/r² force is calculated. Basically,
Exactly.
It's the same
so
thing.
The divisibility of the granularity of the virtual sphere is inversely proportional to whatever. Do you know what I'm saying?
Not exactly. Well, in some ways, it's very simple, which is that the surface area increases by the radius r, and we all know that. But what does that have to do with gravity?
Because if every point is push pull in every direction, the more points you're subjected to, then the more push you're going to be in the opposite direction.
It always sounds to me like you're suggesting that the further away that you are, the bigger your gravity force should be, but that's clearly not the case.
It's the opposite, because gravity is a push and a float, not a attraction and a pull. So on the non-Earth side of you, there is X number of pushes, and on the Earth side, there is fewer because the radius is smaller. So you float away from the greater number of pushes. How does floating work? How do you float in water?
It's an anti-gravity thing, in my opinion, but it's
well, in water, there is omnidirectional vibration, Brownian motion. And I don't know. I don't want to explain floating. I've already stumbled enough trying to explain my vision of gravity. I would just stumble more if I tried to explain without preparation how floating works. I'd use wrong words or bad analogies or something. But like Yeah, let somebody else talk. I'm not feeling like I'm prepared enough to answer the question as presented. I'm not.
That's all right,
doing my
because
job.
this is what we're here for. It's just a casual chat between friends, and if you have, and it just helps you work out. I think how your thinking is.
Well, and yes, you mentioned Lesage, and I would agree wholeheartedly. I'm very much in his camp, not his whole way of thinking, but his view of how gravity works. I'm very much in his camp, I believe, if I understand what his camp is.
Yeah, so that would be the pushing gravity. So, we had started out this discussion with this article about, if you had an asteroid and you're an astronaut, and they basically calculated based on standard mainstream science, how long it would take for those two masses to be attracted to each other. And I was pointing out that, yeah, those very small masses can be attracted to each other. And this kind of was arguing against kind of Lesage type gravity, I suppose. Although you could always say that even in the middle of space, there's something that there's something external pushing.
When you're in outer space, you're not in zero gravity. You're just pulled equally in every direction and pushed equally in every direction. It's just that you're equalized, but you're still very much subject to gravity. I mean, imagine if you had eight very large gravitational bodies, and they were arranged on the corners of a cube, and you were in the center. You ain't going to go anywhere, but obviously you're in a much, much, much denser gravitational field than if you're out in the middle of space, and yet you're not going to accelerate in any direction.
Yes, that would be correct.
And so similarly, when you're in outer space, you're not in zero gravity. There's no place in the universe is there zero gravity. If you're not moving, it's because you're in balanced gravity.
Or something's holding you up. I don't know, like the Earth.
But that's my thoughts on this.
Okay. All right. So you'd be a Lesage proponent. Now, me, I'm the opposite. I don't believe in the Lesage. But only in the sense that actually every attraction is actually due to an imbalance of things being pushed from the outside. So in that way, I would kind of agree, but I wouldn't say I wouldn't.
When we label me as a Lesage proponent, only in that aspect of the nature of gravity being a push versus a pull, and there being shadows versus being objects that magically attract across a gap.
Yeah, so I would, but I'm just saying that that's one legitimate thing, but I still feel that it does actually have to do with the actual mass itself. That gravity is an inherent property due to something which is actually inside the mass. So if I had a lead ball versus a ball made out of aluminum, that the attraction of those two things is different. So you have to be able to explain why is it that the lead ball and the aluminum ball, although appearing to be geometrically exactly the same, have definitely different gravitational properties. So, and I see Bill wants to talk, so go ahead, Bill.
But time out for a second. Bill, is it okay if I continue, because Franklin just brought up a point that I'd like to kind of include and address?
Yes, you can.
Fuck, now I've forgotten it. Say your last part again there, Franklin.
I said if you have an aluminum ball and you have a lead ball, similar size, the gravitational reaction is very different. Now, that I would say that tends very strongly to say that gravity is an internal property, not an external property.
So now imagine existence, every point pushing and pulling in every direction, but then an imbalance and a counterbalance can occur, which will then orbit each other. That creates the harmony between those two, but everything else Is no. Okay, I changed my mind. Let Bill speak.
All right, Bill, go ahead.
Okay. First of all, I'd like to say that from the basis of logic, we have known the origin of gravity for over 100 years. And the person who first did this was Poincaré. And Poincaré showed from logic that he did an expansion of natural philosophy to include what is called meta theory. And meta theory are theorems that apply to all theorems or theories in natural philosophy. And so one of the things that he did is he published the derivation and the proof of these theorems. One of the theorems is no two theories in science, natural philosophy, or physics can employ the same constant and be independent theories. So, for instance, let's just take gravity. Currently, our best theory of gravity, presumably, is Einstein's general theory of relativity. And what are the fundamental constants in his general theory? One of them is c, the velocity of light. Well, c is the fundamental constant of electrodynamics. So gravity, if it's due to Einstein's general theory of relativity, has to have its origin in electrodynamics and cannot be an independent theory. And then there are other theorems that he proved. One is the force, electrodynamic force, the Coulomb force, is a 1 over r squared force. The force of gravity is also 1 over r squared. But Poincaré proved that no two fundamental theories can have the same radial dependence. They have to be unique. Otherwise, they're not fundamental.
Well, is that true, Bill? I mean, it's like it wouldn't be like the volume decay of me speaking would probably also fall over 1 over r squared, but I don't think that we would say that that's an electrodynamic thing. That's more of a geometric argument that applies to anything emanating out of a spherical object. So I'm not 100% convinced that Poincaré is right in this case.
Poincaré proved this, and as a result of that, Einstein's general theory of relativity and also his special theory never received a Nobel Prize because of the arguments of Poincaré. And you've got to realize that. Now, it turns out that the chemists discovered experimentally first the origin of gravity. They were working in chemical laboratories. They were making all kinds of chemical substances, and they discovered that gravity, they were changing the force of gravity in the middle of their process for making these things in their chemical labs. And all they were doing was modifying some electrodynamic properties of the chemicals they were working with. And that made them more massive or less massive. And so they suggested to the physics community, but physics community ignored it because we were in the postmodern philosophy of science where chemistry is in a separate silo from physics. But anyway, they suggested that there was something electrical going on. And when I did my work following the advice of Isaac Newton, who said that the way to make progress in science is to find empirical laws that work in each field and then to solve them all simultaneously if you can and see if you can predict properties in other fields. So, for instance, in electrodynamics, we had 6 empirical equations: Ampere's law, Faraday's law, Gauss's 2 laws, Lorentz's law, and Lenz's law. And when you solve them simultaneously, you get a better version of electrodynamics than we currently have in our textbooks, because they decided to discard 2 of these equations, people like Oliver Heaviside, and just solve the 4 and then make approximations to get rid of the unknown variables that you have in your equations. But I solved all 6 of them. And then when you ask, what is the force of gravity? It turns out that in all forms of matter, you have charge. You have electric charge. You have positive and negative. Every atom has some electrons and some protons. And so you ask, well, what is the force between them that is causing the force of gravity? Well, one of the things that we can measure, but we just never thought about it, is, well, so there's dipoles, and there's quadrupoles, and there's octopoles vibrating in an atom. And we can't stop it. And that vibration will change with temperature. So what you do is you calculate that vibration. So I calculated it, and it turns out that, assuming the atoms are spherically symmetric, that most of the terms in the electrodynamic force between atoms average to 0, but 1 or 2 of them that are minor terms involving V to the 4th over C to the 4th, they are not canceled out by symmetry. And so what we do is we look at the data to see what can we calculate if we take this into effect. Well, we get the force of gravity, and we get big G, but big G depends on the frequency of the vibration and the length of the vibration that is going on in atoms.
So, Bill, let me interrupt you for some moment there.
Yeah.
So how do you explain the difference between the aluminum ball versus the lead ball? So why would the lead ball have a greater gravitational attraction? I would think that, relatively speaking, they would have, I don't know, the same number of atoms. I'm not 100% sure about that. There is some density difference, I suppose. But roughly speaking, about the same number of atoms, maybe the same number, I don't know, dipoles, or however you do it. How do you explain what the difference between a lead ball, say, an aluminum ball would be?
Well, there's a lot of things that can vibrate. You have also crystal structures in those metallic material, and that can affect, because you can have electrodynamic vibrations in those crystal structures, which is something that's bigger than an atom, but you can measure that, and that's why the Russians measured it, and they found the temperature dependence of gravity. And but let me get back to this.
But I think the mass dependence is probably the more interesting thing.
Well, when you derive the force of gravity from the vibration of electric multipoles, quadrupoles, and octopoles, you get a definition of mass. And that definition has to do with the amplitude and the frequency of the vibration of the multipole.
But still not really answering what's the difference between lead and aluminum. Right?
Okay, lead and aluminum have a different amount of electrons and protons, and they also have different crystalline structure. So if we just take the simplest aspect of gravity, which is just the vibration of the dipoles that are within the
and both of those vibrations should be equivalent between the aluminum and the lead, I would think.
Yes, but
They're both same temperature, but radically different reactions to gravity. I mean, a lead ball probably weighs, like 500 pounds, and aluminum ball weighs like maybe 100 pounds.
but
It's quite a difference.
the frequency may be different.
No, the frequency would be exactly the same. If it has any kind of temperature dependence. Now, it
Well-
looks like James has something to say here. So
I didn't explain what we could predict from this. We have been able to predict from this a number of things. One is dipoles that vibrate back and forth, they must radiate energy because they're being accelerated. Anytime you accelerate a charge, you must radiate light, photons. And we see this in our experiments, and all accelerator laboratories see this. It's very standard, well known. And so when we look out into space, and this is something that NASA has done, we've measured the cosmic background radiation, and since most of the universe is hydrogen and helium, can we predict, just from the vibration of these dipoles, can we predict what we observe as the cosmic background radiation? And the answer is yes. We can predict the amount of it, and we can also predict that over time it decreases slowly, and we observe that. And we say, oh, that's just due to the expansion of the universe, but from the Big Bang. That's the way they try to explain it. And but then you have a theory now that predicts the force of gravity, and this theory says the force of gravity, if it's due to the vibration of dipoles, is slowly decaying because it's radiating off this energy. But if we have a body like the sun or the Earth, which is big, it's got a big ball, when the stuff radiates from the center of the Earth, it gets absorbed before it gets to the surface. Only the ones that radiate from the surface of the Earth escape the Earth and cause it to lose its force of gravity. And the answer is the experimental proof of this is, well, over time, particularly a long time, you should have an expansion of the Earth due to the fact that the force of gravity holding it together is decreasing.
And I would really disagree with that. If I have a steel
let
ball,
me finish.
That doesn't expand because there's really no gravitational force on that. That would be presuming that things
Let me
expand.
finish.
But
Well,
I'm just saying, I
our
totally disagree with that.
Our Navy has taken data on the
Well, I know you're going to point out that there is evidence that the Earth expanding, and I would agree with that.
right.
But I would say that there's no connection between decrease in gravity and then the Earth becoming just larger. That does not logically follow.
Okay.
That
Well,
does
let
not
me say
logically
this.
follow
We can now measure
how am I-
the strength of gravity to 8 significant figures, and it is decaying. We can measure every year, it gets less. And so that's what we have. But and if you look in the standard textbooks, for the value of gravity, they don't want you to know that it's decaying, so they only show it to 3 or 4 significant figures. Because
Well, the problem with the force of gravity is that it seems to be, I don't know, if you measure the big G, that people come up with different numbers. As I was pointing out, that G does not appear to be a constant. It seems to be highly dependent upon your experimental setup, which I would predict would be true. I mean, I would agree with you that gravity is an electrodynamic process, but I totally would not agree that it has anything to do with the vibrations of say, dipoles, I would say.
Now, the second thing is we have what we call limestone coral in the oceans. And in the limestone coral, they grow like trees grow, and they have rings, annual rings like trees do. And they have one thing the tree doesn't have too well, and that is a ripple in the ring showing you the number of days in a year. And the data shows that in the past, we had 480 some days in a year, and now we only have 365. And so we know that the Earth is slowing down in its rotation on its axis, and that's due to its expansion. And so now,
Well, that once again may not necessarily follow.
in addition to that, we have measured with Pioneer 10 and 11 the force of gravity as we go out from the sun to the edge of the solar system. None of the theories of gravity, like Einstein's universal law of gravitation, or Newton's universal law of gravitation, or Einstein's theory of general relativity, can explain that characteristic of gravity that we measure. But the dipole electrical dipole vibration origin of gravity completely explains it, predicts it. And not only does it predict that, it predicts the in the spiral galaxies, the outer iron spiral galaxies are moving too fast if theories of general relativity and or Newton's universal law of gravitation are valid. And but this dipole theory of gravitation predicts it precisely. In fact, it says that Newton's laws are not completely accurate, and people have just taken the data and without even any knowledge of what's going on, they have found that there is a modified Newtonian dynamics that appears to be more valid, and that modified Newtonian dynamics is predicted precisely by the dipole and quadrupole and octupole definitions of gravity and mass and that sort of thing. By the way, when Newton was doing his work, he had gravitational mass and he had inertial mass, and he didn't know what they were. He just put a constant in the equation because that was as good as he could do at the time. But now, from this electrodynamic definition of gravity resulting from the vibration of the charges, we can give you an electrodynamic formula for mass and for mass and for gravitational mass. And
all right, that's great, Bill.
So that's more accurate than any other definition of mass we've ever had. And
all right.
So anyway, we have the logical basis saying that gravity should be electrodynamic. That comes from Henri Poincaré, and there's 3 or 4 theorems he has there that all support this conclusion. And by the way, the current scientific community knows this, and they do not allow any library in Europe or America that has the proofs of these theorems by Henri Poincaré to be seen. I went to the University of Maryland in College Park, the world's largest physics department, and I asked, why can't we see this? And they said, we've been told we cannot allow anyone to see it. We are required to either destroy these books or we are to lock them up so that no one, including the president of the university, the chairman of the physics department, no one is allowed to see it. And that is what is going on. And it's because they know that Poincaré's theorems disprove these current theorems in science, but they want those theorems and those theories in science. They do not want to give them up.
Yeah. Okay.
So anyway, that's my little presentation.
All right. So, well, I see we have James here. Hello, James.
Oh,
How
hi.
you doing?
Can you hear me?
We can hear you. I was wondering, what did you
Great.
think about our discussion here? We were talking a little bit about the asteroid and the astronaut, and the article
Yes.
described how they would be attracted to each other. So the question is, why? I suppose the question we've been asking is, is gravity an internal thing or is it an external thing? So some people like to think that it's a pushing thing. But I brought up the challenge. Well, what's the difference between the aluminum ball and the lead ball? The gravitational reactions of those two objects are radically different, but yet they're the same size. And
Why are we saying that they're different when in a vacuum a feather and a lead ball fall at the same rate?
Okay, well, I've collected several comments, and hello, everybody. What Cornelius was saying about every point pushing and pulling, I just wanted to throw into the discussion that with my work in quantization of space, time, and energy, this every point view is archaic, is inappropriate. And that's where we get singularities and infinities. If we look at geometry, a point is just a position in space. And as far as physics goes, it's nothing other than that. And yet we assign things to it happening. So that's probably many of the people here are familiar with my bias or point of view, depending upon how you want to look at it there. Now, with regard to Bill's, I'm going to get to the lead and aluminum balls in just a moment. I'm trying to go quickly here because time is limited. Bill's comments about gravity cannot be a fundamental force, if that's a correct quote that I wrote down, and quote, something electrical is going on, I would have to totally agree with, okay? And just to throw my 2 cents in there. As you may know from what I presented about binary mechanics, we think there's actually a third force beyond the electrical and magnetic, which I call the strong force, which has to do with the bit cycles, which are related to gravity and mass. But I just wanted to put it, as far as the electromagnetic part goes, I have to agree with that. And then Bill was saying something about radiating from the surface. Well, of course, if we go back to my presentation on gravity, I made a big deal about that, about the role of surface temperature and the radiation of quantas of energy, in other words, heat convection, if you will, from the surface as being a key factor in gravity. Now about the lead ball and the aluminum ball. Well, please explain to me. I thought, and I'm perhaps wrong, that if you, the classic experiment, if you go up to the Leaning Tower of Pisa summit, the top of it, and drop the lead ball and the aluminum ball at the same time, they should hit the Earth at the same time.
yes, that's correct.
Now, the last thing, thank you. I want to confirm that I did
But if you
understand
put the
that.
lead ball and the aluminum ball on a scale on the Earth, you find that the lead ball impresses much more force than the aluminum ball does. So there's a big difference there.
Well, yeah, but that's when they hit, and
No, not when
presumably
they hit, but statically.
same velocity, and sure, you would expect a bigger impression.
Well, another difference would be that if you put the aluminum ball and the lead ball in a Cavendish experiment, if you took another test mass and you put it next to the aluminum ball and compared it with the lead ball, you'd find the lead ball attracts the test mass more strongly proportional to its mass than compared to the aluminum ball. So that's another macroscopic thing that you could directly measure with actual experiments.
Okay.
You'd find that the gravitational force coming from the lead ball is much greater.
Now, I guess I'll conclude my little section here, if I may, with just one thought. In the binary mechanics time development bit operations, gravity is considered to be a derivative effect or a derivative force, not a primary force. So I think it's useful in all of the discussion that I've been listening to, which has been very interesting, that there seems to be this tendency that gravity is something. rather than a collection of observations and of different effects that we have seen. And I don't know whether I'm saying that very eloquently, but I think we just get in a hole when we think that every gravity-like effect that we observe is due to something that we call gravity. It's actually a collection of effects, and each one may have its different explanations. For example, in my recent presentation on quantum mechanisms of gravitation, I pointed out that baryogenesis is actually a very much gravity-like effect, and it's probably extremely important in terms of aggregating quantas of mass. That's just an observed effect. I showed the graph in my presentation. So that's what I wanted to say, Franklin, and thanks for giving me the opportunity. And again, hello to everybody. I
But I'm
just
not
get
sure
a little
you
bit.
addressed the difference between the aluminum and the lead ball, other than saying that they both drop at the same rate. We know that, but they if you put them on the scale, you can see that they have a difference in what we measure as weight. And if you were to actually measure directly the gravitational force being emitted by similar sized balls, you would find that somehow the lead ball force is greater than the aluminum ball force, which is still kind of mysterious for given that they're the same size.
Well, the lead ball weight, I'm not sure I'm really prepared to answer that excellent question that you've raised, Franklin, except to say that, well, the density of nucleons in the lead ball, if it's the same size as the aluminum ball, is much, much greater. Okay. So that's why that would explain that it's.
Yeah, but I guess that's the question:
downward.
is like, what would be the difference between the lead atom and the aluminum atom? I mean, it's a couple of, I guess, neutrons and protons, but the question would be, what about that causes that to have a greater gravitational force? I guess. And see then you got to get
but then we're talking about a gravitational force, which I don't believe exists.
But then we have to say that gravitational force.
If we want to talk about forces from my point of view, which is in great part equivalent to esteemed Bill Lucas's point of view about the electromagnetic effects, I have the third force, which is the strong force, which creates cycles of quantum rotation. And for example, for the electron, that is, I believe, the smallest possible solitron in Bill's work, and that's why I find Bill's work extremely interesting and fascinating. The proton bit cycle or hadron bit cycle is much more complicated. And if you've got more nucleons, which are hadron bit cycle, populated with quanta in a particular volume, that's going to be more difficult to move. More difficult to move mean it weighs more. I'll be quiet because maybe I'm not making sense because I'm trying to put all this together myself as well as we speak. So thank you.
That's why we talk about it, because they bring up challenges and you got to think on your feet and help. I mean, myself, when I ask even myself, what is the difference between the lead ball and the aluminum ball, based on my own understanding of gravity, and my understanding of gravity is that is just due to a slight imbalance between the aluminum ball and the lead ball. And both of those cases, both of those things would, generally speaking, be slightly positively charged, because electrons are easily lost off of objects. So, and what is attracting the lead and aluminum ball to anything else is just an electrostatic effect. So, but then what would be the difference between the lead and the aluminum ball?
Well, you were saying that there were experiments showing some big difference between the lead and the aluminum ball, other than what we already know about their weight and so forth. I'm not sure what those experiments were.
Oh, those would be like the Cavendish experiments, where they basically hang a test test mass on like a barbell type arrangement. And then
Okay.
you put like a gigantic concrete block next to that, and you will see that the test mass will be swung over to that, and you by the amount of twisting in the wire, you can tell the
Okay.
amount of force. And by doing that, Cavendish was actually able to directly measure the force of gravity. You know, given the test mass and the mass of the large block, able to directly measure the force of gravity. And I haven't done this experiment, but I would presume that if you had a gigantic block of aluminum or a gigantic block of lead, same size, that you could measure, and those would obviously represent different masses, but you could calculate, you know, what the value of big G is by observing that. But you would see that that the force, I'm presuming,
So
would
so
be
this
much greater
experiment has
with
not
the
exactly
lead
been
block.
done yet. So this experiment
No.
that you're describing has not exactly been done yet. Oh, okay. Well,
No, it has not been done, and
Yeah.
it could turn out wrong. I mean, it could be that the aluminum block and the lead block react similarly, but I think based on the way that they did the experiments, that it would have to be directly proportional to the mass, which is what the gravitational force says, that the force is directly proportional to the mass, that it's G, you know, M2 times M1 over R is the gravitational
okay. My problem
force.
with such an experiment, I guess, or general way to frame things might be that there is no gravitational force. It doesn't exist. Okay, there are only three forces. In my work anyway, the electrostatic, the magnetic, and the strong. And gravity is not one of them. So, you know, to be talking about measuring gravitational force, what you're talking about is a particular effect that you seem to, that one can perhaps relate in one's mind to how
Well, I
difficult
think it's very
it is
obvious
for
that
things to move.
that something's holding my seat to my butt to my chair here. Now, would you generally call that gravity? So I find it, you know, highly disturbing that anyone would suggest that gravity doesn't exist. That would be a very strange thing. Now, I would say that, you know, gravity could be a
Well,
derivative of some other
that's a
force.
gravity-like effect. That's a gravity-like effect.
No, I would
And-
disagree. It's
and-
not a gravity-like effect. That there is, in fact,
Okay,
a force.
maybe that's semantics.
that,
Is that just semantics or what?
No, I think that if there's something which is distinct, like we know that it doesn't appear to be magnetic and that we can't find any north or south pole. It doesn't seem to be strictly electrostatic, and that once again we can't find any positive or negative charge. So it does seem to fall into a specific category of its own, which we call gravity, which only appears to be dependent upon the mass of the object involved. And it's a
But
It's-
I thought if we dropped the aluminum and the lead balls from the Tower of Pisa, they're going to hit at the same time. So it
Yes,
does
but
not
that does-
depend upon it.
no, but that there's still a
I'm saying
very
it-
large
it-
difference.
It depends upon a bit density gradient, as I presented in you know, in the video that's you posted up there.
I mean, it's actually curious as to why that actually happens. And according to mainstream, the reason why they fall at the same rate is because the inertial resistance to acceleration also rises in proportion to the mass. So while the lead ball is actually propelled towards the Earth at a much, much higher rate of much force, and if you measure the amount of force in newtons that is being propelled towards the center of the Earth, it's much greater than the lighter ball, but it's much more difficult to accelerate a much heavier object. Just like if I were to try and push a Volkswagen Beetle, even on a frictional surface, it's much harder to push that than, say, an empty cardboard box on a frictional
Okay.
surface.
So
those
soft-
two balance against each other to cause that, even though the force is much greater on the lead ball than the aluminum ball, cause them to exactly fall at the same rate. Now, not
Well,
unless you
here we're
believe
just inventing
in the,
another. You know, this has been the story in nuclear physics for decades, and I went through and read all the primary source papers. You know, the original publications of the investigators, and whenever something didn't quite fit with with their idea, they'd add to the equations something to cancel out the effect to make it better fit with the data. In other
Yeah,
words,
but
they
what we're
just
talking
invented
about
another
here is
concept.
standard inertial resistance, and that's not something that you add on. That's something that's basically observed. That's Newtonian mechanics. It's very basic. It's not something that they had to bail duck wire and bail it, but it's just kind of interesting. Though. And I would agree that that's why that happens. It's not very complicated, I don't think. Not very much country, but if you're interested in that, you should read up on exactly why that is. It's not the lead and the aluminum ball do not fall at the same rate because gravity affects them the same. It has to also do with inertial resistance. And clearly, when you put them on a scale, they're massively different. Massively different. So that is something you can easily observe experimentally. There is some big difference there. But even like so with my theory, where it's just due to an electrostatic difference, is like, okay, well, so why should the lead ball in general have more of this electrical power than the aluminum ball, right? And it has to do, like you said, perhaps with the number of nucleons in there, although
And the
it
density of them.
doesn't necessarily follow that if you have higher nucleon density, that would imply more chances that you might be missing an electron, right? You would think the missing electron would be
the higher
more.
density. If I can jump in, would relate to how difficult it is to move the object. Okay, it's if all motion is based upon quanta moving from one bit cycle to another bit cycle, and in this case we're talking about the hadron bit cycles, which have to do with most of the mass by far. Certainly, if you've got more hadrons, quanta in hadron bit cycles in a certain unit of volume, that's going to be more difficult to move. Just the probability of that happening is less. So, but I don't want to dominate the conversation. I think what has gone on this week that I find to be a great improvement, and I'll give applause to Franklin, is different people have been participating, and so I don't want to overdo mine. I'm happy to get my little thoughts thrown in there, and I'm very interested to hear what other people think about my thoughts or any of the other thoughts that are buzzing around here. I just don't think it's my summary concept in everything I wanted to say was that I think we run into problems when we consider that or we start to think that gravity is one thing. We observe various effects, and I think each one has to be explained on its own. And certainly Bill Lucas's work seems to be going in that direction, and that's why I'm very excited about his work and would like to look at it more.
Well, one thing that I was thinking about.
I don't want to talk too much here. Let
one
other
thing
people
I was thinking about as we're talking about this, why is it that the lead ball weighs so much more or impresses upon a scale so much more force than, say, the aluminum ball? And so in my view is that the force of gravity is the electrostatic gravity, but it depends upon the dipoles inside of or actually the number of dipoles within the object that you're looking at. So that's a little bit similar to Bill's, that Bill feels that vibrations between dipoles is what causes gravity. I don't believe that that's the case. I believe that what's going on is if you have a dipole inside an object, it can be oriented any which way, but within a gravitational field, it's going to orient it to a very specific way. So it's going to, like if the Earth is positively charged, you have a dipole, then the negative end is going to be pointing towards the Earth and the positive end is going to be pointing away from the Earth. And this is one of the things that I think that you could experimentally show is that according to my theory, if gravity is electrostatic, that you would find that all of the atoms in your body are actually polarized, that they're polarized towards the center of the Earth, or very roughly according to that. So if that were true, then the reason why the lead ball exerts so much more force than the aluminum ball is because inside each atom is composed of these dipoles. Each of the individual dipoles can turn. Now that's that's a little bit iffy, even on because I think atoms are solid objects, so the dipoles within them may not have the freedom to be able to turn around freely. They're all kind of locked together, so maybe the entire atom would have to have some degree of freedom, but that once again kind of iffy. That whether every atom in any object could orient itself to point and polarize to the Earth. That's kind of prediction, but in that way, just the number of dipoles available would increase the force. So, Bill, you have your hand up.
Yes, I want to make one comment. The force of gravity is 10 to the minus 40th power as strong as the Coulomb force. So it's very weak.
Yes, and you know how you can create the force of gravity? All you have to do is take 10 to the 40th hydrogen atoms, remove one electron, and then the force that it creates is the same as gravity. That's all you have to do.
But the other thing is, you have to have a working theory of the atom.
Oh yeah, I got that. I got that's my working atom of
my theory of the atom is the only theory of the atom that predicts more than 50% of the emission spectral lines of all known atoms.
Yes, but we only
with the
I would with all due respect though, Bill, that the problem is that we really only have you to confirm that. It's like I could say the same thing. I could say, no, Bill, my theory explains 100% of every observed spectral sign there is, and that would just be a plain lie. Or I could be completely deluded, and it's a matter of what proof do I have of my claims. Now, I'm not saying that
we have the data, and we have the NASA took the data. They measured in the extreme ultraviolet the spectral lines of.
Yes, we know the data. I mean, but the thing is that what we don't have is something that shows me precisely, where your predictions came from and how that looks like. Because I've looked at the data. That data kind of looks like a scatter plot. I mean, if you look at the ultraviolet thing, it's like they've got a slot in practically every possible frequency in there. So if you were to, it's like you couldn't miss, pretty much.
Well,
it would be my criticism of that data.
It should predict every one of those lines and no others. But
the problem is that the lines were so dense, it basically showed that there was, and this is common, that you predict that you have data and it has data in every single possible data slot. This is the same thing.
Is more precise than the laboratory measured atomic spectral lines. So when you realize that, this is the most precise data we have.
Yes, but it would be more impressive if the data looked like, okay, here's a frequency, and we have a big spike here, and then there's nothing, and then we have a big spike here, and then there's nothing. Just like we see the discrete spectra out of, say, hydrogen or helium. Very discrete, very bright lines.
Those are hydrogen and helium spectral lines.
But what we see in the ultraviolet data is that we see a line like at practically every possible frequency. It just only differs by magnitude.
We're using a grating to divide the light up into the various spectral areas. And so that grating produces some of that width to the lines that you're seeing. The grating does it for laboratory work too. And
I'm not disagreeing with that.
Okay.
But once again, what I'm
saying is that data for the extreme ultraviolet is more precise, more accurate than what we measure in a laboratory for same hydrogen helium atoms. And so you have to understand that. Maybe not being an experimentalist, you don't know about such things, but you
bring us a number of quite remarkable things, and I'm just my only point here is, like I said, with all due respect, is that we really only have your word for it. So, and that may be because
NASA
everything
is
else
their
is,
word for it.
well, the data is from there, but your assertion that you can predict all those lines is something that we
NASA
have to take
judged
your word
my
for it.
son's science fair project and gave it the grand prize at the International Science Fair, which was worth $400,000. They
Yes,
are
that's
willing to spend $400,000 to say, yes, that is a better theory than what we've been doing. Who has spent that much for your work? Or,
or it could just have been the most interesting project that was there. So I mean that's fantastic, and I don't want to say anything to reduce that, but I'm not sure that constitutes a complete agreement with that. So James, you had your hand up.
Yeah, I would like to see that, I appreciate that Bill has published some of his works in various books that you can buy, but I got a little bit of my self into his work by looking at the video that he presented when he was given the Lifetime Award by the Natural Philosophy Org, which is on that site that you can go back and find that video of the talk that he gave and looking at carefully at the slides and so forth. But I would appreciate, and apropos to what Franklin was just saying, that perhaps Bill might want to, I'm not going to denigrate the profit motive to sell books and things like this. That's fine. I have no problem with that at all. But if you're looking for people to really get into your work more and perhaps collaborate, confirm what you're talking about and so forth, or even write about it themselves in a review article or something of this nature, perhaps you could put on the web a basic summary of the equations and almost like a bullet, like a, what do you call it? A PowerPoint type of presentation of just the basics and what you predicted and how, and just get that out there so that it's available to everybody. Well, yes, for free. End of point, period.
well, we already have that at Common Sense Science. We have our
Okay.
website,
I'm writing that down.
commonsense.net, and there are all of the papers in the journal Foundations of Science. Past papers are there, and
Okay. All right.
you can download them. And
Thank you. Okay.
The
It
religious
looks like Ian wants to talk. Go ahead, Ian. We're running short on time, so I'll let
Thank you, Frank. Just a very brief point. I thought I'd get it in before the end, because as you were talking about the difference between, say, the lead bowl and the aluminium bowl, I think one factor which should maybe, lead to a certain degree of skepticism about the simplistic derivation of gravity from electrodynamics or electrostatics is that the gravitational interaction is independent of other factors such as electric conductivity or magnetic properties or optical properties. You could get two balls of exactly the same density which would have completely different electrical properties, for example, or optical properties. And therefore the question perhaps is not quite as simple. I mean, we have to obviously have an open mind about the interrelationship, but the fact that it is quite independent of these other electrical and optical properties, I think should lead to, just a little hesitation in deriving one from the other.
Well, I think that's interesting because that would be an interesting experiment, which is to try and get two substances which have identical density, but have different electrical properties, and then subject them to gravitational tests and see whether they are indeed independent. Because I think one could easily say that if it were more dependent on electrical properties, and say you had something which was like completely non-conductive versus something that was totally conductive, that mainstream and according to the formulas would say that the force of gravity ought to be unchanged. But I think if you actually perform such an experiment, you may in fact find that there is a change. And this is kind of a difference between experiments that we predict and things that might actually happen. Like I said, James pointed out that, no one has actually done the aluminum versus lead ball Cavendish experiment, right? I'm just kind of predicting that, the lead ball would act according to the formulas which we have accepted as mainstream. And similarly, you've proposed another experiment, which is, okay, let's eliminate the density difference, right? Which I'm not 100% sure you could do. Maybe you could do that with a composite kind of object or something. Maybe an aluminum ball versus something which has got, plastic and lead mixed together or something like that. So you get something that has similar density, but very different electrical properties. And then do your gravity experiment and see whether there is a difference. I would say that that in certain, if they'd be very small, but I would think that maybe they are in fact there.
And if you could isolate all these other very, very small effects owing to different electrical properties and so on, that would be a very interesting experiment to do, and the results would be quite interesting to analyze indeed.
Or maybe they'll just find out it's just totally dependent upon the mass, and it just doesn't matter what it's made out of. They do it.
The Russians did their experiment, and they did two types of balls that they measured the force of gravity or the mass of as a function of temperature. One was a crystalline ball, and one was the non-crystalline ball of the same size. And what they found was the crystalline ball had properties that the non-crystalline ball, made of the same metal, did not have.
What were properties of that? Specifically with gravity, did it
What
have
they
any
found
different
was
gravitational?
The two balls weigh the same,
it
Bill?
increase with temperature and then decrease. Increase with temperature and then decrease as you keep heating it hotter and hotter.
Well, that's
And,
between just any ball, but between the crystalline and the non-crystalline. See, I would
Of the
predict.
same metal.
Yeah, I would say
Of the same metal.
that's an interesting thing, because there you have basically the same density, right? James asking would it be the
Right.
same density.
Well,
and
I'm just
crystalline
asking
would
Bill,
be.
the two balls weigh the same?
The two balls weigh the same.
Thank you.
But one ball doesn't change its weight. Oh, I don't know about initially. They didn't compare the two. They took the temperature dependence of the mass of the balls. They measured them separately, but they were the same size ball and the same initial weight, I think. Yes.
Yeah, they could have been
Weight
different
change
weight. I mean,
with one,
it's.
But
So,
not.
Bill, did the crystalline ball react to temperature the same way as the non-crystalline one, or how
No.
did that work?
No.
So, what did the crystalline one do?
The crystalline one, as you heated it up, it started to rise just like the non-crystalline, and then it dropped. The non-crystalline didn't drop. And then it started to rise again as you keep heating it up, and then it dropped again. The non-crystalline one just uniformly rose. It didn't ever drop.
But you're saying that the mass changed. It's not that the mass remained constant and that the gravitational force upon these balls changed. You're saying the mass changed as you performed these temperature changes and so on.
Right, and the mass was measured by its weight, which involves gravity.
Well, that is very interesting. I'm not sure how that would fit into
And that
anybody's
those
theory,
experiments
but
have been reproduced in hundreds of laboratories around the world, and there are many papers on the scientific journals that document that. And
It's a bit circular. I mean, with respect, like perhaps the mass didn't change, you could argue, but merely the gravitational interaction changed.
well, they don't.
maybe.
People who did the experiment didn't know what was causing it. They just wanted you to know there was a temperature dependence, and if you look at the lattice structure of the metal, the lattice has different types of entities in it, and you can see as those entities come apart with a higher temperature, and they're not there to vibrate like they were at the lower temperature, you can see how you get a drop. But you don't see that when there are no lattice structures in the metal. You just have the structures of the interior to the atom, and that doesn't change. So it just goes up uniformly with temperature, because the more higher the temperature, the more energy is in the vibration of the electrons and protons with respect to one another.
Yeah, so that's an interesting empirical result. So we all have to take our theories of how we think gravity works. Like I'm thinking about that going, well, why would the crystalline drop, right? Because the crystalline is much more ordered. And so all the atoms are all pointing in one particular direction. Although it's hard to get a solid crystalline object, I would imagine. Usually metals, they crystallize into small regions is what they do. So a crystalline metal is like that. It's actually kind of difficult to get an actual amorphous metal where it truly doesn't have any crystals in it.
Well, I made those.
I
did experiments in the University of Maryland, College Park, and I took the metal and I made it in crystalline form and non-crystalline form and made measurements on it. Not for this type of experiment, but for a different experiment. And so we know how to do it. We know how to determine if it's a completely amorphous, no crystalline structure, and we know how to make it a pure single crystal. And so that's what we did. And,
and that's very interesting that perhaps the crystalline structure reacts differently to gravity at different temperatures, particularly the drop. I mean, I'm not sure why it would drop and then rise.
The fact that the vibration can no longer be supported because the structure came apart. In other words, each of these structures in a lattice has a certain strength to it, and they're not the same. And so as you heat it up, you break some of those bonds. It's kind of like if I have a bunch of rubber bands and some are stronger than others, and I pull on them, some are going to break, but the rest will still be there.
So are we talking like temperatures high enough to remelt the substance, I guess? To take it from not so high?
We're talking about temperatures from low temperature, say room temperature, to higher temperatures, but below the melting point.
But below the melting point.
Yes.
I wonder if that has anything to do with, say, with the Curie temperature, which is the temperature at which a permanent magnet would be turned to not be a magnet, is another interesting.
There was no magnetic properties of these metals that they did. In other words, they weren't magnetized.
All right, but that just gets me thinking about, okay, that's an interesting data point. I have to figure out why I would think that would be.
Pardon?
What metal was it, Bill?
Lead was one of them.
Oh, okay.
But people have done other metals, and so. I had one thing to tell you that you might want to look up. NIST has measured the mass of 3,000 nuclear isotopes to 8 significant figures. And normally you analyze them by nuclear isotope. Like if you're working with lead, you look at all the lead ones. Or if you're working with iron, you look at all the iron ones. But people have started analyzing it where they look at all with the same atomic weight. Let's say 120. So they might have 25 nuclear isotopes that have an atomic weight of 120, which means they each have different number of neutrons and protons in the nucleus. And so when you plot it, you see you can plot it in such a way that shows you a particular kind of curve, and that curve will tell you what the force that is going on inside the nucleus between these neutrons and protons is. And you can see that it's a 1/r² force for all known nuclear isotopes. And
so no strong force, no weak force.
1/5, and the weak interaction is 1/r³, and neither one, there's no longer any evidence for either one of those in atomic nuclei, and that's all atomic nuclei, over 3,000 nuclear
So
isotopes.
there's another interesting point that, atomic nuclei, whatever they're glued together by, appears to be only Coulomb force,
That's right.
which is interesting. So, but we are at the end of our time here. I've got to head out. So I thank everyone for participating, and we'll see you again next week. All right. So, bye-bye.
Goodbye.